Example 2.3. A 50-gram aluminum disc at 300 degrees C is placed in 200 centimeters cubed of ethyl alcohol at 10 degrees C, then quickly removed. The aluminum temperature is found to have dropped to 120 degrees C. We have the heat capacities of aluminum and ethyl alcohol. A. Physically explain the heat transfer between the aluminum disc and the alcohol. Now draw both a T versus Q and energy bar diagrams for the situation. And then finally, what is the new temperature of the ethyl alcohol? Define the system of the hot disk and cool ethyl alcohol. So with that in mind, then here we go. So we heat an aluminum disk to 300 degrees C and placed into ethyl alcohol at 10 degrees C. So there is a series of events. So let's draw them out. So I have a disk. And we know that this disk is at 300 degrees C. And then we're going to put it into ethyl alcohol, a container. And this is at 10 degrees C. And what we're going to do here is that this is our system. So this is an isolated system. So here's our process now. So that means no heat goes in or out of that system. So now what we're going to do here is that we're going to insert the disk. So when I insert the disk, that means here is that this guy is going to go through a thermal process where now the disk is in the alcohol, and I've dropped this guy right into here. And then what we're going to do is that we're going to remove the disk very quickly. And so when I look at what's happening now, we then have the disk has now cooled down, and we know that its final temperature when it's pulled out is 120 degrees C. And so the question that we're really asking is, what is the temperature of the alcohol? So we're really asking this question. When I look at the temperature of the alcohol, what is it? Right? What is it? Now, just to be really clear here, note that when I look at these guys right here, the system does not reach thermal equilibrium. Okay, it does not reach thermal equilibrium. So they're not at the same temperature. So now that we have a picture, let's move on now. So now what we want to do here is that we want to carefully map out the energy transfer. And the way we're going to do that is that one thing that we'll do is that we're going to draw a bar diagram. And two, we're going to plot T versus Q along with its bar diagram. So here we go. So remember, the bar diagram is to give us a conceptual understanding of what is going on. So the first thing I'm going to look at here is I'm going to look at bar diagram. So what do we know here? We know that heat energy is transferred out of the hot disk and into the ethyl alcohol, into the ethyl. So then the first law says what? It says that the heat lost of hot disk now does what? It changes the internal energy of ethyl. But when you change the internal energy of the ethyl, there is a temperature change. And so therefore, this is the heat gained by the cool ethyl alcohol. So if I start to map this thing out here, so I'm seeing here that there's a heat loss due to the hot disk. All of that then changes the internal energy of the ethyl. And the way we visualize it is that now there's a change in the heat transfer of the ethyl alcohol. So the first law says this right here. Right? So again, this tells us about what? This is the heat loss. Over here, this is the heat gained. But I want to do this in a series of pictures to give you a sense of what is going on. So here's what happens here. So the bar diagram looks something like this. So the bar diagram looks like this. So the first thing I'm going to do here is that I imagine that the internal energy of the ethyl alcohol is low. So this guy's going to be ethyl at its initial state, and it's a low energy state. And then what we're going to do here is that we're going to transfer heat from the disk. So if I transfer heat from the disk, what you're seeing here is that now there's a heat loss due to the disk. And as a consequence, I now have an internal energy that has now increased by the alcohol. So this here is the final internal energy of the alcohol, which is now higher. Now I can redraw this a little bit different here. And the way I'm going to redraw this here is that, look what I'm going to do. I'm going to bring the internal energy of ethyl in its initial state over to the right. So my picture then reads like this. So this here represents minus Q of the disk. And what did that heat do? What it did here is that it changed the internal energy of the alcohol. So when I look at this, this is the ethyl alcohol, state 2, whereas this is the lower internal energy of 1. And you could see that I essentially subtract them. And you know what? I drew this wrong because it should have been below the axis, because it's a negative quantity. So it should have been down right here. So what you're seeing here in this plot here is that this right here now equals the change in internal energy of the alcohol. So when I look at this guy, this is really the change in internal energy of the ethyl. So when I look at that boxed equation, it's this quantity that then tells me that this is the heat gained by the ethyl alcohol. So these two, this is what that really looks like right there, picture-wise. So now the next thing that I want to do here on 2 here is that now I want to plot T versus Q with a horizontal bar diagram. So let's go do this here. So what I'm going to do here, so I want to try to draw a nice big one here. So let me go 2, 4, 6, 7. And then I think I'm going to set my central axis right here. So this is the temperature, and then this is the heat right here. So now let's go look at what happens. The alcohol starts off, the disk starts off at 300 C. And then I'm going to say it's going to drop here to 120 degrees C. So when I draw a line here, I'm going to say that this line right here is my 120 degrees C. Now look at this thing. Look at the heat of the disk. It's negative. So what you're seeing here is that if this is my 300 degrees C, I'm going to say that the slope of this curve looks something like this. So this line is the heat decreasing to 120 degrees. So this is the hot disk cooling as it transfers the alcohol here. So now let's look at this guy here. This thing right here is my 10 degrees C. Now note that this is not the scale, of course. So this line here represents when you pull the disc out, right? So this is when the disc is pulled out of the ethyl alcohol. But remember, what we said up here is that it never reaches equilibrium. So if I was to look at the line of the alcohol, what it does here is that it is cooler than the 120. So it comes to here, and so it's going to take some time for it to get up to this temperature, let's say. So this is the ethyl heating up. So now let's look at the heating. So the heat that you see here is that I have heat due to the disk. So how much heat is transferred from the disk to the alcohol? It's this amount. So note that this is now a horizontal bar diagram. So this is the heat loss due to the disk. But if I look at that, this is exactly how much heat is going to be transferred to the alcohol now. So if I look at the bar, you could see here that this represents the energy transferred to the ethyl. So just in summary here, let's say it. So the first thing that we're seeing here is that the disk cools from 300 degrees C to 120 degrees C. This implies that you have a negative slope to show cooling. And then what you have here is that you have the ethyl heats up from 10 degrees C to some unknown temperature. But this implies that you're getting a positive slope to show heating. And that's what that graph is doing right there. So now if I move this up here, I could now, so my goal here is that, so if I look at B, we want to calculate the final temperature of the ethyl. And the way we could think about it is we could think about it this way. So the final temperature of the ethyl should be the temperature initially of the ethyl times the change in the temperature of the ethyl. So ultimately, what we really want to compute is we want to compute this change because we know what the initial temperature was. So now, the data given is what? We have the specific heat and the mass of each of the objects here. So if you think about this, I have the mass and specific heat of the aluminum, which then tells me that I have a mass of aluminum, which is equal to 50 grams. And I know that the specific heat of aluminum is going to be 900 joules per kilogram degrees Celsius or Kelvin. And then I have the stuff for the ethyl alcohol, and they tell us that the mass of the ethyl is equal to 158 grams, and its heat capacity is 2400 joules per kilogram degrees C or Kelvin. So now I'm going to follow right through the first law. So from the first law, we know this. We know that the change in internal energy of the ethyl is now seen as the heat change, or as the heat transfer to the ethyl, which now deals with the temperature change. And then this guy is minus equal to that of the disk. So now if I put that all together, what this really tells me here is that I really have the mass of the inertial mass times the change in the temperature of the ethyl, and that's going to be minus times the thermal mass of the aluminum disk times its change in temperature of the aluminum. So now what I'm going to do here is that I'm going to solve for the change in temperature for the ethyl. So if I do that, here's what I get. I have the change in temperature for the ethyl is then going to be minus, then I have the ratio of the aluminum divided by the ratio of the ethyl alcohol, times the change in temperature for these guys. So now I'm going to just plug in my numbers. So if I plug in my numbers, this is going to be 0.05 times 900 divided by 0.158 times 2400, and then the change in temperature is 180 minus 300, and this will be in degrees Celsius, but it could be degrees Kelvin. And so when I compute this, I get positive 21.4 degrees Celsius for the change in temperature for the ethyl. So now that I have this, I can now compute the final temperature. So then the final temperature of the ethyl alcohol is then going to be T ethyl 2, which will be T ethyl 1, its initial temperature, plus the change in this. And this should give me 10 degrees C plus 21.4 gives me 31.4 degrees C, which then gives me the final temperature.